Hi class, this is Dr. O'Connor, and in this video I'm going to go through sections 3.1 through 3.5. So let's talk a little bit about ionic compounds, and then we'll talk about ions and some periodic trends, and then we'll get into the nomenclature or the naming of these ions and compounds. Anyway, it turns out that some compounds that are composed of alkali metals and halogens will form these salts. So here we have potassium iodide, and that's added to salt, table salt, to provide iodine. Sodium chloride, we're all familiar with that. Of course, it's table salt. Sodium fluoride is added to water so that we have fluoride ions. And sodium iodide is used to detect radiation. So the compositions and the properties of these compounds are very similar to one another. We have a 1-to-1 ratio of metal to nonmetal. They all have high melting points. They are stable, and they're all white crystalline solids, and they're soluble in water. If we were to add one of these four salts to water, the salt would dissolve, and a water solution that contains one of these compounds will conduct electricity. It turns out that electricity can only flow through a medium that contains charged particles that are free to move around. Those charged particles in this case are called ions, and that is going to be the topic of these first few sections. So we'll talk about why a water solution of these salts will conduct electricity in a moment. So we all know that atoms are electrically neutral. What that means is they have equal numbers of protons and electrons. In other words, the positive charges equal the negative charges. Now, it turns out that atoms can either gain or lose electrons. When an atom gains an electron or loses an electron, it becomes charged. So here we define an ion. An ion is an electrically charged particle. We can have positively charged ions or negatively charged ions. A positively charged ion is called a cation. Let's take a look at sodium. So we have a sodium atom, and we know that Z is equal to 11. That means the sodium atom has 11 electrons and 11 protons. It's neutral. Now, what happens when that sodium atom loses one electron? Let's take a look here. The sodium atom, when it loses one electron, now has 10 electrons and 11 protons. That means there is a net charge of a positive 1. And the symbol for the sodium ion would be written like this, where the plus indicates a positive charge. We don't include the 1. That's just assumed. So, for example, let's take a look at strontium with Z equal to 38. How many protons? Well, 38. How many electrons in that neutral strontium atom? 38. Well, it turns out that strontium, which, by the way, is in group 2A, loses 2 electrons. Let's write the symbol for that. So when strontium loses 2 electrons, there are 36 electrons left. But we still have 38 protons. So that means we have a net charge of a positive 2. So we would write the symbol for strontium like so. Let's talk about anions. These are negatively charged ions. So for example, the chlorine atom. It has 2 electrons in an S subshell, 5 electrons in a P subshell. The chlorine atom has 17 protons and 17 electrons. If the chlorine atom gains 1 electron, now it has 18 electrons and 17 protons. So that means it's going to have a -1 charge. And we write the symbol for the chloride ion like so. Let's take a look at some more symbols. So potassium, it will lose 1 electron to form the potassium ion. Calcium will lose 2 electrons to form the calcium ion. Notice the +2 charge. Bromine will gain 1 electron to become the bromide ion, and oxygen gains 2 electrons to become the oxide ion. Notice how we name these. When an atom loses electrons, we just keep the atom's name and add the word ion. So here we have potassium ion, calcium ion. When an electron is gained, then, for example, bromine, it gains an electron to become bromide. We add the IDE suffix. Oxygen gains 2 electrons to become the oxide ion. Let's take a look at these problems. Here we're told that iron atoms can lose 2 electrons when they react. Write the symbol of the resulting ion. Is this a cation or an anion? Well, if iron loses 2 electrons, then it's going to have a +2 charge. This is a cation. Remember, cations are positively charged ions. Sulfur atoms gain 2 electrons. Write the symbol of the resulting ion. If sulfur gains 2 electrons, it will have a -2 charge. This is the symbol. And of course, because it's a negatively charged ion, this is an anion. Let's take a look at something called the Octet Rule. And the Octet Rule states that main group elements tend to undergo reactions that leave them with 8 valence electrons. So let's take a look at this. Here we have sodium, and this is the electron configuration for sodium. And notice there's 1 electron in the 3s subshell. Then we have chlorine, and this is the electron configuration for chlorine. And notice there are 5 electrons in the 3p subshell. Now, when sodium and chlorine react, here's what happens. Sodium will transfer that 3s electron to the chlorine atom, and that electron will go into the 3p subshell. So what we have is sodium ion, and it has 0 electrons now in the 3s subshell. So it's left with the neon configuration. And notice that when the chlorine atom gains 1 electron, when that electron is transferred from the sodium atom to the chlorine, it now has a full outer shell. That electron goes to that 3p subshell. Notice that outer shell has 8 electrons. Same here with the sodium. Notice that the outer shell, when it loses the electron, has 8 electrons. So we can also represent that like this. Sodium has 1 valence electron. Chlorine has 7 valence electrons. And when that electron is transferred from the chlorine, or from the sodium to the chlorine, we end up with sodium ion and chloride ion. What happens is a metal will transfer an electron or more than 1 electron to a nonmetal. Both the metal and nonmetal will resemble the valence shell configuration of a noble gas. That means there's a full outer shell. Having 8 valence electrons leads to stability and lack of chemical reactivity. I mean, let's face it, table salt, which is sodium chloride, is very stable. So main group metals will react so that they attain an electron configuration like that of the noble gas just before them in the periodic table. Let's take a look at that, what that means. So we saw the sodium, it lost one electron and it acquired the noble gas configuration of neon. Magnesium in group 2A will lose 2 electrons, and again, it will acquire the noble gas configuration of neon. The nonmetals will react so they attain an electron configuration like that of the noble gas just after them in the periodic table. So for example, here, the chlorine gained an electron and attained the electron configuration of argon. Oxygen will gain 2 electrons to attain the noble gas configuration of neon. So for example, if I were to tell you that calcium loses 2 electrons to become calcium ion, then you should be able to write the electron configuration for that calcium ion. In fact, let's do it this way. Let's go ahead and write the electron configuration for calcium. So what we have is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Now, when calcium loses 2 electrons, it'll lose them from the 4s subshell. Then calcium ion will have the following electron configuration: 3s2, 3p6. And this is the same configuration as argon. Okay? Let's take a look here at fluorine. And the electron configuration for fluorine is, let me erase this, is 1s2, 2s2, 2p5. Fluorine will gain 1 electron and it becomes the fluoride ion, and its electron configuration is 1s2, 2s2, 2p6. That's the same electron configuration as neon. Practice those. So I would expect that you can write electron configurations for ions. Here this shows part of the periodic table, and let me tell you what happens with the main group elements. The elements in group 1A tend to lose 1 electron. The elements in group 2A tend to lose 2 electrons. In 3A, really the only element that loses 3 electrons is aluminum. In groups 4A and 5A, we really don't have any common ions, except for nitrogen. Nitrogen can gain 3 electrons to become the nitride ion, and also phosphorus can gain 3 electrons to become the phosphide ion. In group 6A, the nonmetals, oxygen, sulfur, and so on, they tend to gain 2 electrons to become ions. In group 7A, your halogens, they gain 1 electron to become ions. And group 8A, those are the noble gases. They have 8 electrons, so they're fine. They don't lose or gain electrons. So this just shows us, so a group 1A metal, okay, it will lose 1 electron to become a positively charged ion. Group 2A, we have a +2 charge. Group 3A, a +3. And then we go to group 6A, and they tend to gain electrons to become ions, 2 electrons. Group 7A, 1 electron to become ion with a -1 charge. Again, in group 5A, nitrogen can gain 3 electrons and so can phosphorus to become the nitride and the phosphide ions. Okay? Now, the transition metals, on the other hand, they will form cations. All metals can form cations. But what can happen is they can lose, in addition to their s electrons, they can lose one or more d electrons. So for the transition elements, the octet rule is not followed. But the octet rule is followed for the main group elements. Metals, again, lose electrons. Nonmetals gain electrons. So metals form cations by losing one or more electrons. And so group 1A and 2A metals form +1 and +2 ions respectively in order to achieve that noble gas configuration. Transition metals can form cations of more than one charge by losing a combination of valence shell s electrons and those inner d electrons. Reactive nonmetals form anions by gaining one or more electrons in order to achieve that noble gas configuration. Group 6A nonmetals form -2 anions. Group 7A elements, they form -1 ions. Group 8A elements, the noble gases, do not react. We can predict the ionic charges of the main group elements using the group number and the octet rule. For 1A and 2A metals, cation charge is equal to the group number. Same with 3A. For nonmetals in groups 5, 6, and 7A, the anion charge is 8 minus the group number. So for 6, the elements in group 6A, like oxygen, it gains 8 minus 6. That's 2 electrons for a negatively charged oxide ion. Let's take a look at this problem. Which of the following ions is likely to form? Here we have a sulfur with a -1. Let's go take a look at, if we take a look at the periodic table, we'll see sulfur is in group 6A. It's going to gain 2 electrons in order to attain a noble gas configuration. So this sulfide ion with a -1 charge will not exist. Actually, sulfide ion looks like this. Here we have a bromide ion, but with a -2 charge. It's in group 7A. It only needs to gain 1 electron to attain a noble gas configuration. So this would not form, but this one would. Calcium ion. Well, calcium ion is in group 2A, and therefore it would only lose 2 electrons to attain a noble gas configuration. This would not form, but this would. And then we have the phosphide ion, and that is in group 5A, and 8 minus 5 is 3. So yeah, phosphorus can gain 3 electrons to become the phosphide ion with a -3 charge. So this one's good. Here they're asking us to write the electron configuration for the nitride ion. And hopefully you have your periodic tables in front of you. Okay, I don't have one here. But we know the nitride ion gains 3 electrons. It's in group 5A. So its electron configuration will be 1s2, 2s2, 2p6. It will attain the electron configuration of neon. Okay, let's take a look at some periodic properties and ion formation. And we're going to talk about something called ionization energy. Let's think about it. In order for an electron to be removed from an atom, remember that's being held and attracted by the nucleus, it's going to take some energy in order to do that. So the ionization energy is the energy that's required in order to remove 1 electron from a single atom that happens to be in the gas phase. So in other words, in order to pull that electron away, we need to provide some energy. It turns out that the less energy required, the more likely the cation is going to form. So low ionization energies, and we abbreviate that IE, will favor the formation of cations. A high ionization energy will not favor the formation of cations. Electron affinity. It turns out that when one or more electrons is added to a single atom in the gas phase, there is energy that is released. That's mainly for those non-metals. Okay, because remember, non-metals tend to become anions, whereas metals tend to become cations. Non-metals are going to have much higher ionization energies than the metals. The electron affinity, of course, is going to be higher for a non-metal than it is for a metal. So we can see the trends here on this graph. On this graph, what we have is ionization energy increasing as we go up. And here we have atomic number. Elements are arranged by Z. And look at these peaks and these valleys. And what this tells us is that when we go down a group on the periodic table, the ionization energy decreases. So in other words, it's easier to remove an electron from potassium than it is from sodium. Also, this shows us that as we go across a period on the periodic table, the ionization energy increases. So for example, it's going to take more energy to remove an electron from aluminum than it is sodium. Alkali metals have the lowest ionization energies and lose an electron most easily. Halogens, they're way over on the other side of the periodic table, have the highest ionization energies. That means they gain an electron most easily. So let's take a look at the periodic trends. As I said, you move down a group, ionization energy decreases. You know, there are always going to be some exceptions, but all we need to know for now is in general, as we go down a group on the periodic table, the ionization energy decreases. When we move across a period, the ionization energy increases. Why would it increase as we move across a period? That's because as you go across a period, the atomic radius will decrease. So in other words, a fluorine atom is smaller than an oxygen atom. Well, what does that mean then? That means that those electrons, those outer electrons, are closer to the nucleus. The closer they are to the nucleus, the more difficult it is to remove those electrons. Metals tend to lose electrons and non-metals tend to gain electrons. The main group elements towards the middle of the periodic table, boron, carbon, nitrogen, tend to not gain or lose electrons, although nitrogen is an exception. Okay, we'll talk about the types of compounds that we find, boron, carbon, and so on, in a little bit later. So let's go ahead and take a look at a problem. Again, you should have your periodic table out. We're asked which element in each pair has the lower ionization energy, magnesium or calcium. Well, calcium is below magnesium on the periodic table, so it would be calcium. Magnesium or aluminum. Magnesium is in group 2A, aluminum is in group 3A. It'd be more difficult to remove an electron from aluminum than calcium or magnesium. So magnesium has the lower ionization energy. What about electron affinity? Which has the higher electron affinity, oxygen or fluorine? Fluorine is further to the right of the periodic table than oxygen, so it would be fluorine. So let's see how we name main group metal cations. And actually it's pretty easy. For the main group metal cations, all we do is identify the metal and tack on the word ion. This is potassium ion, magnesium ion, aluminum ion, sodium ion. For the transition elements, and also those elements like tin and lead and indium, they can form more than one type of cation. We use two naming systems. There's the old one and the new one. In the new system, the charge on the ion is given as a Roman numeral in parentheses right after the metal name. So here we have chromium with a +2 charge, We would call that chromium. In parentheses, we put the Roman numeral 2 and add the word ion. Chromium 3 plus, that'd be chromium. In parentheses, put the Roman numeral 3 and then tack on the word ion. In the old naming system, and you need to know about this because, for example, for supplements that contain iron, it's usually in the form of iron 2 sulfate. But rather than list it like this, what they do is they call it ferrous sulfate. So the ion with the smaller charge is given the ending OUS, and the ion with the larger charge is given the ending IC. So here we have chromium 2 ion. The old system, we would name it chromous ion. And chromium 3 ion would be named chromic ion. It has the higher charge, so it gets the IC suffix. Here's a table with some of the more common transition metal cations, and it shows both the old and the new names. So here, copper can have a +1 or a +2. The +1 is called cuprous. The +2 is cupric ion. Here in the new system, we name it as copper 1, copper 2. I just talked about iron. The iron +2 is the ferrous, and the iron +3 is the ferric. Here we have mercury. Okay, notice here there's a +2 charge, but there are 2 mercury atoms. This one here would be mercury 1 ion. And the reason mercury 1 is because this particular cation has the 2 mercury atoms. Each one has an average charge of a +1. Here, this would be mercury 2 plus. So that would be mercury 2 ion. Tin, which happens to be in group 4A, it can have a +2 or a +4 charge. So this would be the tin 2 ion. This would be the tin 4 ion. So practice naming these. As far as anions, we name them by replacing the ending of the element name with "ide," followed by the word ion. So here we have bromide ion. Here we have chloride ion, fluoride ion, iodide ion, oxide ion, sulfide ion. Let's take a look at this one. What would the name of this ion be? Well, this occurs when selenium gains 2 electrons. This would be the selenide ion. That's it for this video, and I will get the other video together. We're going to be naming ionic compounds. You do need to know how to name these ions, and you will also need to know how to name the ionic compounds. Everybody have a great night, and if you have any questions, again, as usual, please contact me.